Hi there students, and welcome to lecture 3 of the LN 2016A Electronics 1 course. I'm your lecturer Mohammed Dango, and today we'll be going through analyzing diode circuits. We'll start off by looking at the ideal diode model, followed by the first and second approximations of the diode, the piecewise linear analysis, iteration, or if you Prof. Hofsayer, iteration analysis, and lastly the graphical analysis. This can all be seen in your textbook, chapter 1, pages 34 to 41, and note that anything said or done in this lecture can and may be used as a question in the test or examination. A bit of a recap from a long time ago. Students, the resistor characteristic curve, Ohm's law, V is equal to IR. If we plot it with current on the y-axis and voltage on the x-axis, we know that the gradient of the curve, which is the change in current over the change in voltage, gives us 1 over the resistance. Now, similarly, if we look at the diode characteristic curve, which was introduced in lecture 2, here we have the plot. I'm sure you guys remember that our diode can operate in the forward bias region when we connect a source to the diode, and the positive terminal of the source is on the anode and the negative terminal of the source is on the cathode of the diode. We operate in the forward bias condition. Important points in the forward bias condition is the diode on voltage. This is the point at which our diode starts to conduct and switches on. We then have the reverse bias condition when we set up our diode circuit with a source and the positive terminal is on the cathode end and the negative terminal is on the anode end. We are in the reverse bias condition. And in the reverse bias condition, a saturation current of the order of microamps starts to flow through our diode, and we can see that here in our saturation region. And if we were then to decrease this bias voltage to a point where it reaches our breakdown voltage that we see here, it's approximately minus 50 volts in a silicon diode. We then reach our breakdown region. As you know, we discussed avalanche breakdown in the previous lecture, and we see massive amounts of saturation current start flowing through our diode once we go below the breakdown region. Now, the thing about the diode characteristic curve is, although it's a very beautiful curve, it's quite a difficult curve to use to analyze our diodes, because it's modeled by the diode equation, which was the final equation I introduced in the second lecture. So in order to make things a bit simpler and make things easier for us to analyze diode circuit, we can do an ideal model of our diode. Now, the ideal model of the diode simply looks like this, and it models the diode as a circuit component known as a switch. Now, students, you're probably familiar with a switch. And this switch that you see here can have two positions. Here in the forward bias region, the switch is considered to be closed, and that's because our diode is on. And here in the reverse bias condition, no current can flow, and that is why the switch is open, so it has infinite resistance, so no current flows in the reverse bias condition. And that, students, is basically the ideal diode model. We model the diode as a switch. In the forward biasing condition, the switch is closed, current can flow. And in the reverse biasing position, the switch is open, no current can flow. Now then, let's look at some circuits with our ideal diode model. Here we have a very simple circuit which has a source connected to our diode and a resistor in series with it. Very simple 3-component circuit. And our source, we have a time varying signal that you can see here. Look at that. And what happens is we now model our diode, which means we're going to replace this diode component in our circuit with the ideal diode model. And as we know, when our input voltage is greater than 0, we're going to be forward biasing our diode. So we replace our diode circuit element with a closed switch. And when our input voltage is less than 0, we are reverse biasing our diode, so we simply replace it with an open switch. And that is how we then model our diode in an actual circuit. And what does the output voltage, or the voltage across this resistor, look like when we take a measurement? Well, students, here we have it. So if you were to go into the lab and take your multimeter and measure the voltage across this resistor, you would see an output voltage that looks like this, because our diode only conducts in the forward biasing condition, and in the reverse biasing condition, when our input voltage is less than 0, this is not allowed to flow, and therefore we have what is called a rectified output across our resistor. Now, the thing about this ideal diode model, which is simply modeling our diode as a switch, is, yes, it's simple, but because it's so simple, it's not very accurate. And that leads us, students, to the diode first approximation, which we see here. Now, we are very well aware of this diode on voltage. Yes, remember your barrier potential voltage. Yes, it's the same as this diode on voltage. For silicone, it was 0.7 volts. So what we do with our ideal model is we simply shift the forward biasing graph to the point where we are at our diode on voltage. And this is what the result looks like. There's no change happening here in the reverse biasing condition, but now the diode, which was being modeled in the ideal case as just a switch, now with the first approximation is modeled as a switch in series with some source. Yes, and this source that you see represents our diode on voltage. For the case of a silicone semiconductor, we know that that is 0.7 volts. Now, because this first approximation has a straight line, that means there's no gradient, and we don't have any diode resistance in this case. So the diode first approximation, to remind you, it's just modeling our diode as a switch, which is an open switch in reverse bias, in series with a source. And that source represents our diode on voltage. And in the forward biasing condition, it's a closed switch in series with our source, which represents our diode on voltage. Now, what does the diode first approximation look like in an actual circuit? So again, we've got two very simple circuits that are built. Diode resistor source. In this first circuit, we are forward biasing our diode. You can see positive terminal connected to the anode. And in the second circuit, we are reverse biasing our diode, so negative terminal connected to the anode. So with the forward biasing, we replace our diode with a closed switch and in series with a source. In the reverse biasing condition, we replace our diode with an open switch in series with a source. And we know that the source is 0.7 volts for silicone. So let's do a little bit of KVL. I'm sure you guys remember your KVL from circuits. Yes, we do KVL. That gives us this first equation. Input voltage is equal to the diode voltage plus the resistor voltage. We replace the resistor voltage with the current multiplied by the resistance, and then we simply solve for our diode current. Easy peasy, guys. You should have done quite a bit of this in your circuits course, and that is the diode first approximation. Now, the thing about the diode first approximation is, yes, it's a bit more accurate than the ideal diode model, but it's not as accurate as it can be. That leads us to the diode second approximation. And basically, with the diode second approximation, we simply add some gradient to this forward biasing curve so that it can have a change in current over change in voltage, which represents our diode resistance. Now, students, every single circuit element has some resistance which impedes the flow of current. This is true from your wires to your batteries to your diodes to your actual resistors. They all have some sort of a resistance. And the diode second approximation takes this resistance into account for our diode circuit element. So now when we model our diode according to the diode second approximation in the reverse bias condition and in the forward bias condition, we see that we replace our diode circuit element with a switch that is closed for the forward bias condition in series with that source which was from our diode first approximation, which is the VD on, and in series with some resistor. Yes, this is our diode's resistor denoted by RD. So our diode has been replaced by a closed switch, a source, and a resistor in series for the forward bias condition. And in the reverse bias condition, yes, very similarly, we have an open switch in series with our diode on voltage, represented by this little battery or source, in series with our diode resistor, which is RD. Now then, when we take our diode characteristic curve and we model it using these straight lines, as shown here, it is what is called the piecewise linear model, because we're taking pieces of straight lines and we're using them to approximate what's going on with our diode curve. Now, of course, this approximate is not an exact solution for our diode, but it is good enough. And that's why we use the piecewise linear model to analyze diode circuits, because it's quite a good approximation. And here we have an example to take us through the piecewise linear model. We've got a very nice circuit with a source in series with a diode, in series with a resistor, nice and easy 3-element circuit. So consider the circuit shown, let the input voltage be 8 volts, and assume piecewise diode parameters of, wow, they've actually given these to us. Diode on voltage of 0.7 volts, must be silicone, diode resistance of 10 ohms, and then go ahead and draw the equivalent piecewise linear model circuit and determine the power dissipated in the diode. Let's get cracking. So first off, the equivalent piecewise linear model circuit, we see that our diode is in the forward biasing condition because the positive terminal of the battery is connected to the anode. So we replace this diode circuit element with a closed switch in series with our diode on voltage, represented by the source, in series with this resistor for our diode resistance, and we can now perform a KVL in this nice circuit that we see here. So from KVL we get our first equation. Input voltage is equal to the diode on voltage plus the voltage dissipated across the diode resistance plus the voltage dissipated across the resistor. If we take this a step further, we replace this with Ohm's law. So we get our diode current multiplied by our diode resistance, diode current multiplied by our resistor's resistance. VD on and V in stay the same. We then rearrange the equation to make the diode current the subject. We know all these terms, substitute them in, 66 milliamps for our diode current. Now that we have our diode current, it's a very simple thing to calculate the diode voltage, which, don't forget to take in account the diode on voltage plus the voltage of the current multiplied by the diode resistance. So it is this total voltage of the source and the diode voltage across the resistor. It's these two voltages put together that sum to give you VD. And we then plug everything in and we get a nice 1.36 volts. And then finally they've asked us to actually calculate the power dissipated across the diode. You guys know power is equal to voltage times current. Take the current, take the voltage, multiply them together, 90 milliwatts. That's the power dissipated in the diode. Now, that covers it for our piecewise linear model. and how to solve diode circuits using the piecewise linear model. Next up, we have the iteration analysis. Now, this is a bit more difficult than the piecewise linear model, but with this difficulty or complexity comes a bit more accuracy. We have our same 3-element diode circuit, source in series with a diode, in series with a resistor. And if we perform a KVL in the circuit, Vin is equal to Vd plus IDR. If we rearrange this to make our diode current the subject, we end up with this. And now, if we go back to our diode equation from lecture 2, you guys remember this very important equation, we then combine the two and make the input voltage the subject, and this is the equation that we end up with. And this is the equation that we're going to be solving for the iteration analysis. So how do we go about doing that? Let's demonstrate it through an example. Consider the circuit shown. Let the input voltage be 4 volts, the resistance be 4 kilo ohms, and the saturation current 10 to the minus 12 amps. Determine the diode voltage and current using the ideal diode equation and the iteration method. So here we have the equation that we had from the previous slide that we got from substituting in the diode current from KVL into the diode ideal equation. And if we were to plug in everything to this equation, you'd see that the only unknown is the diode voltage Vd. The left side of the equation, we have a number 4. So now what we do is we start trying different values of Vd. And we plug it into this equation and see what we get out on the right side until we get a number that is very close or equal to the number on the left side. So I started off with 0.5 volts, and when I solved the right side of the equation, I got 1.399. So that tells me I need to go up with my Vd value, which I did. I took it all the way up to 0.75 volts, threw it into the equation, and I got a very large number, 13,483. So that tells me that the Vd value lies somewhere between 0.5 and 0.75. So because I got such a big value here, I made a smaller jump for my third iteration of 0.55, and the right side of the equation solved to 6.7 volts. So I'm still greater than 4 volts. So I had to reduce this 0.55. I took it down to 0.535, chucked it in, solved the right side of the equation, and look at that. I got 3.99 volts, which is what we're looking for. So therefore, the diode current can then be calculated because we have our diode voltage of 0.535 volts. We throw it into this equation and we get 0.866 milliamps as our diode current. And that, students, is the iteration analysis of a diode circuit put into practice. Now you must note that if you are asked to use this iteration analysis method, you have to be given the saturation current or enough terms to calculate your saturation current. And then you simply use this equation over here and keep solving the right side till it equals the left side. Students, now that we've covered the piecewise linear analysis and the iteration analysis, the final analysis that I'm going to be covering in this lecture is the graphical analysis. Once again, we have this very simple 3-element circuit, a source forward biasing our diode in series with a resistor. Taking KVL, we have the input voltage is equal to the diode voltage plus by the current multiplied by the resistor. And if we rearrange this to make the current the subject, as we did previously, we now have what is called the load line. And this is a linear graph that we can plot on our diode characteristic curve to help us figure out what our diode current and voltage is. So, in order to determine the x-intercept of this graph or this load line, we set our diode current or current to 0, and that means our input voltage is equal to our diode voltage. That gives us our x-intercept. If we set our diode voltage Vd equal to 0, we can then calculate what our y-intercept is, which gives us our current input voltage is divided by our resistor. And of course, the slope of this graph is -1/r. So let's actually plot this through a demonstration. Here we are, graphical analysis in action. Consider the circuit shown. Let the input voltage equal 4 volts. The resistor is 4 kilo ohms. And determine the Vd diode voltage and diode current ID using graphical analysis. So here we have our load line equation. We set ID equals to 0. Our x-intercept is 4 volts. That's over here, 4 volts. We then set Vd equal to 0 to determine our y-intercept, and that gives us an ID value of 1 milliamp. That is over here. We then plot from 1 milliamp to 4 volts, and we see where our load line intersects with our diode characteristic curve. And that point, students, is known as the Q point. And at the Q point is where we get our answer. So from the Q point, we then go down to our x-axis, and we get 0.5 volts for our diode voltage. That was very close to the iteration example, and 0.8 milliamps, which is also very close to our iteration example. So, graphical analysis, students, this analysis only works if you have the diode characteristic curve, which is plotted on appropriate axes, and then you can get your load line from whatever circuit it is you're trying to solve, plot your load line, and the point at which it intersects the diode characteristic curve is the Q point, and from the Q point you can determine your diode current and voltage. And that, students, brings us to the end of lecture 3. To recap, we went through the ideal diode model, which simply meant modeling a diode as a closed switch when forward biased and as an open switch when it was reverse biased. We then took a look at the diode first approximation, which took into account the diode on voltage, and through the diode first approximation we now model a diode as a closed switch in series with a source for forward biasing conditions, and that source has a voltage of whatever the diode on voltage is. And for the reverse bias condition, the diode first approximation has an open switch in series with a source that has a value equal to the diode on voltage. The diode second approximation took it a step further and added some resistance to our diode, and we now could model our diode in the forward biasing condition as a closed switch in series with a source in series with a resistor. And for the reverse biasing condition, through the diode second approximation, we modeled our diode as an open switch in series with a source in series with some resistor. And we noted that when we model our characteristic curve of the diode using straight lines, that's known as piecewise linear analysis. It's the simplest analysis, but that makes it one of the least accurate analysis. The second analysis was the iteration analysis, where we had to solve the diode equation, but we had to have access to the saturation current in order for the iteration analysis to work, and we basically kept solving the right side of the equation until it equals the left side of the equation, and that allowed us then to figure out what's happening in our diode. And finally, the graphical analysis, which could only take place if we have access to an appropriate graph for our diode. We determine our load line through KVL, and we then set up the load line so that we can figure out what the x-intercept is and the y-intercept is, and the point at which our load line intercepts our diode characteristic curve is the Q point, and it is at the Q point that we then solve the current and voltage for our diode. So students, that's the end of our lectures for week 1 of this course. I hope you've taken notes and you've got some questions for me to come to the lecture enrichment session on Thursday. I look forward to seeing you all and to answering your questions. Remember that you can look at your textbook, chapter 1, pages 34 to 41, if you need any more information on these different analysis methods that I've covered in the lecture today. I appreciate your time and thank you.